Hello students, welcome. Now we will see Miller indices for directions. So what is mean by Miller indices? That should be the first question. So as we know that crystalline materials are having atoms, they are arranged in periodic fashion, and suppose they are arranged in a direction, that periodicity continues to the finite distance, that we call as crystalline material. So we can designate these atoms by a vector. We can designate the position of atom by a vector. Miller has introduced a system for that, for designate the atoms, that we known as Miller indices. The indices is a plural of index, that is a set of three numbers. These three numbers will designate the position of that particular atom or the particular direction or the particular plane along x, y and z axes. So there are three basically types of Miller indices. First is for atoms. This is the symbol for writing the Miller indices, such as dot, M, N, P, dot. M and P are the position coordinates of atoms or points, and dot is a symbol for representation of that. For direction we use a square bracket, and U, V, W are the indices along x, y, z axes. For plane we use a round bracket and denote the position of the plane or the index of that plane by H, K and L. So we will see now one by one. Before that, you have to remember that indices is a plural of index. Negative value are indicated by a bar over the number. So what we have written here is 101 bar, and this is, since this is a square bracket, so this notation is for Miller indices of direction. 1 bar meaning that this axis is along minus z, and this is very important thing, that Miller indices are never in a fraction. You cannot write Miller indices in a fraction, or you cannot get an answer of anything in a fraction. If you are getting that, it means you are doing something wrong. And the last one is, it do not have any comma. If you have comma, that simply represents the position coordinate. But if you have a double integer, then you can use comma. For example, 1, 0, 12. So 1, 0, 12. This is a Miller indices for direction. Now there is a family of this directions, atoms and planes. That family we can denote by another symbol. For atoms, the symbol is double dots. For direction, that symbol is a triangular bracket, and for planes, that symbol is a curly bracket. So for example, if you write 1, 0, 0, this means that it is a single direction, and if you write 1, 0, 0, it means that it is a family of direction. What is the meaning of family, or what is mean by family? Family is the direction or the planes or the atoms having same magnitude but in opposite or any direction. So 1, 0, 0 is for single direction. I can also write this as minus 1, 0, 0. These two belongs to the same family. The only thing is that this is along positive x-axis, this is along negative x-axis. That is the meaning of family of directions and planes. Now we will revise the concept from the 12th class, the position coordinate of atom. Suppose we have a BCC unit cell. This is the BCC unit cell. There is an atom at the center. Then there is atom at each corner. For example, we have the origin at this position. Origin we also denote by 0, 0, 0. It means that the position of this particular atom or this particular point is 0 along x-axis, 0 along y-axis and 0 along z-axis. It means that it is at the origin. Then if you go along x-axis, you have to write 1, 0, 0. It means that this position of this atom is 1 along x-axis, 0 along y-axis and 0 along z-axis. It means that it is lie only on the x-axis and not on y-axis and z-axis. Similarly, for this point it is 0, 1, 0. It means that it is lies only on y-axis. Similarly, for this 0, 0, 1, it means that it lies only on the z-axis. Now, if you have an atom in between these planes, then the position coordinate will change. For example, for this one, for this atom lies in between x and y plane. This lies between x and y plane. For position coordinate of x is equal to 1 and position coordinate of y is equal to 1. So how to get this? First you have to start from the origin. Now we have to go to this point. We have to start from the origin and we have to go to this point. So we have to go along x-axis, then along y-axis and then along z-axis to find out the position coordinate. So from origin we will go along x-axis first. We have reached here. This is 1, 0, 0. From here we will move along y-axis. Then we will reach here. This is, since this is x-axis is 1, so 1 is already there, and then y-axis is 1. So we have traveled 1 unit distance along x, and then from that 1 unit distance along y. The position coordinate is 1, 1, 0. Similarly, for this one, we have traveled 1 unit distance along x, then 1 unit distance along y, and then 1 unit distance along z. So that's why the position coordinate is 1, 1 and 1. Similarly, you should try for other position of atoms also. If you don't understand this, you won't understand the directions and planes easily. Now, since you know the position coordinate of atoms, I want you to try to find out the Miller indices of given points. Remember that for points we have a symbol like this, M, N and P. So I will show you for one of the point and then you can find out for others. This is the origin here. We will find out for point number 7 for this point. So to reach at this point I have to travel along x, then along y and then along z. Here you can consider the length as unit distance. So first I have to travel along x, 1 unit distance along x. I have reached here, and then I have to go to the point number 7, that is along z axis, so that I have to travel along z. Then I will reach here. So x equal to 1, y equal to 0 because I don't have to travel along y, and then z equal to 1. They have to write in 2 points. So this is the Miller indices for atoms at point number 7. Similarly, you should try for other points also. Now, how to use the Miller indices to find out the direction, or if the Miller indices are given, how to draw the direction or how to show the direction. So there are two cases we will consider here. First case is when the direction is given. It means that we have given a unit cell. In that unit cell there is a direction or there is a vector. You have to find out Miller indices for that vector. So first step is you have to find out the coordinates of head and tail. Remember that whenever there is a vector, suppose this is a vector always have a head and tail. Wherever the arrow is, it will be always head, and the back side is always tail. So first you have to find out the position coordinates of head and tail. Then you have to subtract tail from the head. Further, pair the fractions reduced to the lower integer because Miller indices are never in fraction, and then enclose in a square bracket. This bracket is because this is a symbol for representation of direction, and write bar over negative integers. Remember that Miller indices should always be in integer. Before moving further, let me tell you some important thing, that if you have a negative indices or you have a negative direction, you have to move your origin. For example, this first we will see in 2 dimension and then we will move to the 3 dimension. So we have x-axis here, we have y-axis here. The opposite of this will be the negative x-axis. The opposite of this will be the negative y-axis. Similarly, in this case, the opposite of this will be negative x, opposite of this will be negative y, and opposite of this will be negative z. Right? We consider this as the origin. If we consider this as the origin, the cube or the unit cell has 8 corners, and we can take any of the origin from that unit cell. So I will draw here one unit cell. This is unit cell. So it will have 1, 2, 3, 4, 5, 6, 7, 8. These 8 corners I can take as a origin depending on the situation. Suppose I have given a Miller indices called as 1, 1, 1 bar. So it means that this is along x, this is along y, and this is along minus z. I need to have a negative z axis in my unit cell. If I don't want to include in my unit cell, I have to show another unit cell. Sometimes you may have to show 2 to 3 unit cells for representation of the plane or directions. That we want to avoid. That's why we will move our origin to get this indices into our unit cell. So just now we have learned that this is x, this is y, and this is z. Opposite of this will be minus x, opposite of this will be minus y, and opposite of this will be minus z. Now we want minus z into our unit cell. So we cannot take this as origin, because if we take this as origin, negative z will go outside. So we can take this as origin. So if we take this as origin, this is x, this is y, and this is z. So negative z will be now inside the unit cell. Now we can show this direction inside the unit cell. This is very, very important. I want you to try few examples before moving further. So I have given one example here. There is a symbol here called plus symbol. You have to find out the position coordinate or the points coordinate of this symbol respective to the different origins, and the direction is given here, is given in this schematic. This is x-axis, this is y-axis, this is z-axis. So if we consider this x, this y, and this z, then the Miller indices for points to this plus sign is equal to x equal to 1. I will come here, then from here y equal to 1. So it will be respect to O, with respect to O. So 1, 1 and 0. Now if you take O as origin, so x will be out, minus x will be inside unit cell. Now for respect to O1, this will be x, so minus x will be the inside unit cell, this is y and this is z. So with respect to O1, the Miller indices for this plus sign is equal to 0, 1, 0. Similarly, you can try for other position coordinates, then you will know the utility of shifting the origin inside the unit cell. Now we have given a direction that is shown here in the black color or blue color, whatever you can say. This is the direction. These are the axes x, y, z. You have to find out the Miller indices for this. Origin is given here, so this is x-axis, this is y-axis, and this is z-axis. First step is you have to choose the coordinates of tail. Tail coordinate is, because that is the origin, so it will be 0, 0 and 0. Then coordinates of head 1, 0, 0. Head minus tail will be 1, 0, 0. Clear fractions, there are no fractions and closing parenthesis. So this Miller indices for the given direction is 1, 0, 0. Another example here. This is x-axis, this is y-axis, this is z-axis. Coordinates of tail. So to find out the coordinate of tail, you have to move to that particular point. So I have to move at this point. First I have to move along x, then along y, and then along z. So I will come to this point by moving along x 1 unit distance, then moving along y 1 unit distance, and then moving along z 1 unit distance. So coordinates of tail are 1, 1 and 1. Coordinates of head, because that is the origin, so it will be 0, 0, 0. Head minus tail will be minus 1, minus 1, minus 1. Clear fractions, no fractions, and closing parenthesis. Third example. In the third example, we have to find out the coordinates of head and coordinates of tail. So first, for coordinates of tail, half unit distance along z, and then 1 unit distance along y. Half unit distance along x, 1 unit distance along y, 0 unit distance along z. For coordinates of head, it will be x. No, I don't have to travel along x-axis, I don't have to travel along y-axis, I have to just travel along z-axis 1 unit distance. So it will be 0, 0, 1. Head minus tail will be minus half, minus 1 and 1. Clear fractions, minus 1, minus 2, and closing parenthesis. So the Miller indices for this given direction is minus 1, minus 2 and 2. Now we will take the second case. In the second case, when the Miller indices is given. So now you have given a Miller indices, for example 1, 2, 3, and you have to draw the corresponding direction in respect to this. So for this, the procedure is, first you have to choose the origin, then mark the point, join the origin and the last mark point, and show a vector representation. So now first we'll show 1, 1, 0 direction. 110 means this is x, this is along y, and this is along z. So 1 unit distance along x, I will come at this point. From this 1 unit distance along y, I will reach at this point. 0 unit distance along z, I don't have to move from here, so I have to join this and show an arrow. Now 1, -1 and -1 direction. Now first you have to choose the origin. Now I want minus y-axis and minus z-axis inside the unit cell. So I will, because this origin will not give me the negative indices for minus y and minus z, so I don't want to use this origin, or we need to shift the origin in a such place that this direction should come inside the unit cell. So I have to choose this point as the origin, then this will be x direction, this will be y direction, and this will be z direction. So minus y and minus z and plus x are all three inside the unit cell. So first 1 unit distance along x, I will come at this point. From that -1 unit distance along y, I will come at this point. Then -1 unit distance along z. Since z is on the top side, that is outside the unit cell, minus z will be inside. So this with the ending point. So join this with respect to the origin and show the vector. Now you have to remember one thing, that if you have a bigger integer than 1, or if you have any index greater than 1, you have to divide by that particular index and then mark the respective axes. This is because otherwise you have to show then 2 or 3 unit cells.